Greetings, everybody. Learning is a hobby here. I wanted to finally make the video for the exercise set for section 5.6 in Tao's Analysis 1 book. So we're going to finally finish up chapter 5 in Tao in this video. So let's do that, and then I'll explain, we'll get back to Spivak after this, so I'll explain that at the end. So let me jump right into the exercises. Okay, so there's only five exercises in this exercise set, but the first two questions have a bunch of parts to them, so they're kind of long. The rest of them are relatively straightforward. In fact, even starting at question two, going forward, the questions are very quick and straightforward. The only real, I guess, difficult uh, question in this section is the first question. Let's go through it though. In question 561, Tao asks us to prove lemma 5.6.6, um, which is a lemma from if you look back in my video for the summary for section 5.6, you can see what that says. I have the different parts of the lemma written out here, so I don't have to go back to the summary to show you. But Tao does give us a hint here. Actually, he gives us a hint for several of the parts. He says, review the proof of proposition 5.5.12. Let me show you that real quick, what that says. 5.5.12 is the proof where we show that there is a number that squares to give you 2. Where is it? That's this proof here. So there exists a positive real number x such that x squared equals 2. And then this is the proof in the summary for section 5.5. So he says, take another look at that proof because we're going to do something similar here. Also, you'll find proof by contradiction a useful tool, especially when combined with the trichotomy of order in proposition 5.4.7 and 5.4.12. The earlier parts of the lemma can be used to prove later parts of the lemma. And then finally, with part E, first showed that if x is greater than 1, then x to the 1 over n is greater than 1. And if x is less than 1, then x to the 1 over n is less than 1. We have to break it up into those two cases. You'll see in a second. We have to break it up into those two cases because the nth root x differently, depending on whether x is bigger than 1 or less than 1 or equal to 1. So let's go through the proof. All right. By far the I guess the most tricky one of all of these parts is part A in this proof. Let me read out the hypotheses here that will hold for all of the parts. Let xy be greater than or equal to 0 be non-negative reals, and let nm be greater than or equal to 1 be positive integers. And then part A says this: if y is the nth root is x to the 1 over n, then y to the n is equal to x. So we know that x to the 1 over n is defined to be the supremum of the set E that I have written on the next line, but we don't yet know that when we raise that to the nth power that it actually indeed is equal to x. So here's the proof for that. Let y equal x to the 1 over n and E equal the set of all z in R such that z greater than or equal to 0 and z to the n less than or equal to x. Then let's say y is the supremum of E. Assume for the sake of contradiction that y to the n is not x, then there's two possibilities. Either y to the n is less than x or y to the n is greater than x by trichotomy of the real numbers. And here we take it by cases. So assume y to the n is less than x. Then here I'm defining this number m to be the maximum of this sequence of numbers here, and choose k, y to the k, where k goes from 0 to n minus 1. You'll see why I'm picking that in a second. Then there is an epsilon in R such that epsilon is strictly between 0 and 1, and y to the n plus nm epsilon is less than x. We can do that by the Archimedean property. Then y plus epsilon to the n by the binomial theorem is given by y to the n plus summation k going from 0 to n minus 1, and choose k, y to the n minus k, epsilon to the k. Now, I do have to make a note here. We haven't talked about the binomial theorem in Tao's book yet, but the binomial theorem can be proved using induction, and we've done many proofs by induction in this book. Furthermore, we've proven by induction the binomial theorem in Spivak, so I felt comfortable using it here. Um, but I guess technically you should, if you're going to use the binomial theorem, I guess you should, just to be in the spirit of the book, you should prove the binomial theorem first um, using induction, right? But anyway, uh, y plus epsilon to the n is equal to this by the binomial theorem, which is less than y to the n plus n m epsilon, which is less than x, by the way, that we chose epsilon. That shows that y plus epsilon is an element of E, and this contradicts that y is the supremum of E. All right, so case one doesn't work. Case two, let's check next. Assume y to the n is greater than x, then there is an epsilon in R such that epsilon's between 0 and 1, and y to the n minus nm epsilon greater than x. Again, you could do that by the Archimedean property. Then y minus epsilon to the n is equal to, again, by the binomial theorem, y to the n plus summation k going from 0 to n minus 1, negative 1 to the k, and choose k, y to the n minus k, epsilon to the k, which is greater than y to the n minus n m epsilon, which is greater than x by the way that we chose epsilon. That means that y minus epsilon is an upper bound for E. However, this contradicts, again, that y is the supremum of E. So the only thing that's left by trichotomy is that uh, y equals y to the n is equal to x, right? So it has to be, the only thing that's left is equals. All right, that's the proof for part A. Here's part B. If y to the n is equal to x, then y is x to the 1 over n. Let y to the n equal x. Assume alpha is the supremum of E and 0 less than equal alpha less than y. We had a theorem from a previous section that said that we can do that. We can always find a rational. Um, oh, sorry, no, this is not the part. The second part is from the theorem. There's some rational R between alpha and y. We can always find a rational that satisfies that because we're assuming that alpha is less than y. There's a theorem in a previous section that says we can do that. Okay. So alpha to the n less than r to the n less than y to the n equals x implies r is an element of E. This contradicts that alpha is an upper bound for E. Therefore, y equals sup E since it is an upper bound for E, and there's no real number less than y that is an upper bound for E. Okay, part C says x to the 1 over n is a non-negative real number and is positive if and only if x is positive. And since x to the 1 over n is the supremum of that set, that's how we defined x to the 1 over n. For any y in E, that implies y is greater than or equal to 0 and less than or equal to x to the 1 over n. Therefore, x to the 1 over n must be non-negative. Assume x to the 1 over n is greater than 0, then there's some rational r. Again, we had a theorem that said we could do this such that 0 less than r less than x to the 1 over n, which implies 0 less than r to the n less than x, which implies that x is positive, which means x to the 1 over n is less than or equal to 0. Sorry, if x to the 1 over n is less than or equal to 0, then for any y in the set, I'll call that set E because I basically call it E for the remainder of the things. So if y is an element of the set E, then y is less than or equal to x to the 1 over n less than or equal to 0, which implies y equals 0. So that implies y to the n is 0, which is x. Okay, part D says if x greater than y, if and only if x to the 1 over n is greater than y to the 1 over n, right? So x to the 1 over n greater than y to the 1 over n greater than 0 implies x to the 1 over n to the n greater than y to the 1 over n to the n greater than 0. That implies that x is greater than y by proposition 5.6.3 and part A. Okay, and then for the reverse part of the biconditional, we can do it by contrapositive. If 0 is less than or equal to x to the 1 over n less than or equal to y to the 1 over n, that implies x is less than or equal to y by so proving proving the contrapositive uh, can be done using a similar method to what I just did in the first part. So I just didn't write it down. Okay, part E, there's actually three parts to part E, and I have them listed one, two, and three. Actually, I don't think I did part three here. because it's relatively straightforward. I'll show you when I get to it. But anyway, here's the first part. If x is greater than 1, then for any positive integers kl, where k greater than l, then x to the 1 over k is less than x to the 1 over l. So let x be greater than 1. So first thing I have to do, I'm using Tau's hint here. I have to show that if x is greater than 1, then x to the 1 over n for any positive integer n will always be greater than 1 as well. Um, okay, so let x greater than 1 and n a positive integer and e be that set. Let m be the maximum of n choose k, k going from 0 to n minus 1. Then there's an epsilon from 0 to, between 0 and 1, such that 1 plus nm epsilon less than x. Then 1 plus epsilon to the n by the binomial theorem is 1 plus yada yada. And that's less than 1 plus nm epsilon less than x by the way we chose epsilon. Therefore, 1 plus epsilon is an element of E, and since x to the 1 over n is the supremum of E, that has to be greater than, right? Because 1 plus epsilon is greater than 1. Okay, and now we can prove the theorem. Let KL be positive integers such that K is greater than L. Assume for the sake of contradiction that X to the 1 over L is less than or equal to X to the 1 over K. Then 1 less than X, which is equal to X to the 1 over L to the L, less than or equal to x to the 1 over k to the L. X to the 1 over L to the L is equal to x by part A and B, right? Implies 1 less than x less than or equal to x to the 1 over k to the L, which implies that 1 is less than x to the k, less than or equal to x to the 1 over k to the L to the k. And the last part in that triple inequality can be simplified to x to the L. Therefore, 1 is less than x to the k is less than or equal to x to the L. However, x greater than L implies that L is k minus m for some m in n. Then x to the L is less than x to the L times x to the m, which is x to the k. So x to the L is less than x to the k, but that contradicts the fact that we found that x to the k is less than or equal to x to the L. Therefore, x to the 1 over k less than x to the 1 over L. So proof by contradiction, right? Part two I skipped because it's similar to the first part, but the proposition says this: if x is less than 1, then for any kl positive integer such that k greater than l, x to the 1 over k is greater than x to the 1 over l. Like I said, I skipped the proof for that because it's similar to part one. There's also part three that I actually just forgot to write down, which was, let me just show you here. Let's see, part E is over here. So this is the third part over here. If x is equal to the 1, then x to the 1 over k equals 1 for all k. And this follows, straightforwardly, right? Because 1 to the k is equal to 1. That implies that 1 equals 1 to the 1 over k. So I forgot to write it here, but really, it's simple proof anyway. So anyway, that's part E. So part F is pretty straightforward. Part F says xy to the 1 over n equals x to the 1 over n times y to the 1 over n. Here's the proof. Xy is equal to xy to the 1 over n to the n by part A and B of 5.6.6. And xy equals x to the 1 over n to the n times y to the 1 over n to the n. And that implies that x to the 1 over n times y to the 1 over n, all raised to the nth power, equals x to the 1 over n to the n times y to the 1 over n to the n, which is equal to xy to the 1 over n to the n. And that implies that x to the 1 over n times y to the 1 over n is equal to xy to the 1 over n by proposition 5.6.3. That's from the summary, the summary for section 5.6. Okay, in part G, x to the 1 over n to the 1 over m is equal to x to the 1 over nm. So again, here's my proof. X to the 1 over nm to the 1 nm is equal to x, which is the same thing as x to the 1 over n to the n. That implies that x to the 1 over nm to the m is equal to x to the 1 over n, which is equal to x to the 1 over n to the 1 over m to the m power. And that implies that x to the 1 over nm is equal to x to the 1 over n to the 1 over m by proposition 5.6.3. Okay, and that's the first question. The question one is really the hard one of the bunch. The rest of them are really we'll go quick. 5.6.2 has a bunch of parts to it though, but each of the parts is relatively simple. So 5.6.2 says this, prove lemma 5.6.9. And then he gives a hint. He says you should rely mainly on lemma 5.6.6. That's the one that we just proved, and on algebra. And there's a bunch of parts to it. So here's the hypothesis that'll hold throughout the problem. Let xy greater than 0 be real numbers and qr be rational. Part A says show that x to the q is greater than 0. Right, so here's the proof. Let q be n over m for nm integers where m is not 0. Then x greater than 0 implies x to the 1 over m is greater than 0 by proposition 5.6.6. And x to the 1 over m is greater than 0 implies x to the 1 over m to the n is greater than 0 by proposition 5.6.3. Then x to the q is x to the 1 over m to the n, which is greater than 0. Right, like I said, these are going to be quick. Part B, they want us to show these two properties of exponents where now Q and R are rational. I didn't prove the second part because it's very similar to the first part, but I did prove the first part explicitly. If you want to prove the second part, like I said, it's very similar to the proof that I have here, but I skipped it. So just because I didn't feel like writing it out. So let Q be M over N and R be S over T, where M, N, S, T are integers and T not 0. Then X to the Q plus R is equal to X to the MT plus SN over all over NT. That's just by, if you remember the way that we defined addition of rational numbers. And that's equal to X to the 1 over NT raised to the MT plus SN, which is X to the 1 over NT to the MT times X to the 1 over NT to the SN. And that's equal to x to the 1 over n to the 1 over t to the mt times x to the 1 over t to the 1 over n to the sn. And then it just simplifies to give you what you want, which is x to the q times x to the r. Also, like I said, the second part is shown similarly, but I skipped the proof of it here. I just didn't feel like writing it out. All right, part C says x to the minus q equals 1 over x to the q. And here's the proof. It's one line. So 1 equals x to the 0 is x to the q minus q, which is x to the q times x to the minus q, which implies that x to the minus q is the multiplicative inverse of x to the q, or in other words, x to the minus q is 1 over x to the q. Right, part D, if q is greater than 0, then x greater than 0 if and only if x to the q greater than y to the q. And here's the proof. Let q equal m over n and x greater than y if and only if x to the 1 over n greater than y to the 1 over n by prop 566, and x to the 1 over n to the m greater than y to the 1 over n to the m by proposition 5.6.3. Therefore, x to the m over n greater than y to the m over n if and only if x to the q greater than y to the q. And that's the proof. Right, part E, if x greater than 1 and x to the q greater than x to the r, if and only if q greater than r. If x less than 1, then x to the q greater than x to the r, if and only if q less than r. I think I only proved one of these because they're both very similar. So here's the proof. Let x greater than 1, q equal m over n, r s over t. Here I didn't write it down, but we can assume whether or not q and r are negative or positive or 0, we can always assume that the denominator is a positive number. I didn't write that down here, but there was a theorem that we had that said that. So such that q is greater than r, then because of that fact, we can say that mt over nt is greater than Sn over nt, because we can assume that n and t are positive numbers. That implies mt is greater than Sn, which implies that x to the 1 over nt raised to the mt power is greater than x to the 1 over nt to the Sn power, which is greater than 1, because x is greater than 1, right? Implies x to the q greater than x to the r. And then the other one is proven similarly, but like I said, I skipped it because it's similar to the one we just did. All right, part F wants to show that xy to the q is equal to x to the q, y to the q. I'll skip going over the proof here. You can pause your screen here if you want to see it. It's like a one-line proof as well. So that proves all the parts in question number 2. All right. The rest of them are, like I said, are very straightforward and pretty quick, actually. So we'll go through these quickly. 5.6.3 says this: if x is a real number and n is an even natural number, then n equals 2m for some natural number m. Show that x to the n is greater than or equal to 0. So I broke this into three cases. Case one, if x is 0, then obviously 0 to the n is 0. So 0 to the n is greater than or equal to 0. Case two, if x is greater than 0, then x times x is greater than 0, which is, but x times x is the same thing as x squared. That follows by proposition 5.6.3. And then case three, if x is negative, in other words, x is less than 0, then x times x is positive. Um, but x times x again is equal to x squared, so that's greater than 0 by proposition 5.6.3. Okay, therefore, for any x in R, x squared is greater than or equal to 0. Next, let m be a natural number. Then x to the 2m is the same thing as x squared to the m, which is guaranteed to be greater than or equal to 0 because x squared is greater than or equal to 0. So the result follows from proposition 5.6.3. Okay. 5.6.4 is one-line proof as well. If x is a real number, show that the absolute value of x is x squared to the 1/2. So here's my proof. Since x squared is greater than or equal to 0, then x squared equals the absolute value of x all squared. That follows from, again, proposition 5.6.3, I think, says there's a part of that that says that. That implies x squared to the 1/2 is equal to x, the absolute value of x squared to the 1/2, which simplifies to give you absolute value of x. Therefore, the proposition follows. That follows from proposition 5.6.6. Okay, and then last question, 5.6.5. Again, relatively quick proof. Let me read out the problem first. If x, y are positive reals and q is a positive rational with q greater than or equal to 1, show that maximum x to the q, y to the q equals maximum x, y to the q. And same thing for the minimum, where the operations min and max are defined in exercise 5.4.9. And then Tau asks us what happens if we have q less than 1 instead of q greater than or equal to 1. So I don't think I proved the second part just because it's similar to the first part. So I just did the first part, and you can, if you want to try the second part, you can do it. It's very similar. Here's the proof. So let x, y be real numbers that are positive, and let q be a rational number that's greater than or equal to 1. Then I have two cases here. Assume x is greater than or equal to y. Then by proposition 5 point, what is it? 5.6.3, x to the q is greater than or equal to y to the q greater than 0. That implies that maximum x to the q, y to the q is x to the q, but that's the same thing as maximum x, y to the q. Right? And case two is very similar. Assume y, excuse me, assume y is greater than x, then y to the q is greater than x to the q greater than 0 by proposition 5.6.3. That implies y to the q greater than x to the q greater than 0. Sorry, did I write that twice? That implies that maximum x to the q, y to the q is equal to y to the q, which is the same thing as maximum x, y to the q. And like I said, the other part is for minimum is proven similarly, so I just skipped it. And then to just answer Tao's question, if q is between 0 and 1, including 0 but not including 1, then the same result holds. If q is less than 0, then the maximum and minimum operations just switch. So max x to the q, y to the q is the minimum of x, y to the q, and minimum x to the q, y to the q is maximum x, y to the q. And that's the end of chapter 5. So let me stop my screen share. Okay, so we're done with Tao's chapter 5, which means I'm going to finally move back to Spivak's book, and we're going to do the construction of the real numbers in Spivak using Dedekind cuts instead of Cauchy sequences. So the next video will be the first part of the construction of the reals in Spivak. Once we finish that, just to give an outline of what's coming up, once we finish the construction of the reals using Dedekind cuts, we'll go back to chapter 9 in Spivak, and we'll finish up the book for Spivak. Then, so that that covers derivatives, integrals, sequences, and then once we do that, we'll finish up Tau. So we're going to finish up both of these books, but I'm going to finish up Spivak before I finish up Tau. All right. And then once we finish both of these, we'll talk about that when that happens. So I just to give you another just heads up, I do have the video for the next experiment in Charles Platt's Make Electronics, his book. I have that coming up this week sometime, so keep an eye out for that. The Spivak video should be coming out by the weekend, and I have some vlog stuff for the upcoming holidays for the month of December on the way. So I do have, even though I took a little bit of a break there, I have some stuff coming out in December, and we should over the winter I should be able to pick up my video schedule again for a while. So thanks for watching, guys. I'll see you in the next video. Give me a like and subscribe, and I'll see you hopefully this week, before the weekend. So, all right, take it easy, guys.